Hello, I'm Sebastien Durif, and I will present you the results of the PhD of Taher Al-Dafaea, supervised by my colleague Bouchair and myself. The presence of large web openings is frequent in steel construction, as they allow to pass through the web different kinds of ducts and they permit an optimization of the global structural weight. However, the presence of large web openings imply various specific failure modes, such as the global shear or bending failure of the net section, the Eurosteel mechanism, and the web post buckling, and others that are illustrated here. Therefore, a solution widely used by constructors is to reinforce the openings with different types of stiffeners. They can be vertical on the web panels or horizontal on the opening members, or a combination between vertical and horizontal stiffeners, like a kind of frame stiffening solution. The present work is mainly dedicated to experimental tests on large web openings. Two experimental test campaigns have been conducted. The first campaign that I will present you aims at studying different stiffening solutions for an isolated large rectangular opening, mainly submitted to Eurosteel bending. The second test campaign aims at studying the behavior of various opening shapes under a point load, which is located at the mid-length of the opening. Here are the three studied stiffening configurations for the first test campaign. You can see that we have short stiffeners, which length is equal to the opening length, and long stiffeners with an anchorage length called LA. Both of these configurations can have either a single-sided or a double-sided stiffener. The third configuration consists of a combination of vertical and horizontal stiffeners, which makes a kind of frame stiffening solution. Those stiffening configurations are regarded for openings of 300 and 200 mm high. Thus, we arrive to a total of 12 beams that have been tested. The experimental tests were conducted at the Civil Engineering Laboratory of University Clermont-Auvergne. The beams were submitted to three-point bending using a hydraulic jack of 900 kN of load capacity. The objective is to observe Eurosteel failure of the openings and the influence of various stiffening solutions on its behavior. Various displacement measurements have been used to describe the vertical deflected shape and to detect a possible local buckling in the most compressed part of the opening. Finally, various strain gauges have been arranged on the beams to compare numerical and experimental results. Here are first results on the beam with an opening of 300 mm high, without stiffener at the left and with a short single-sided stiffeners at the right. We can see that both configurations show very similar results, with some ductile behavior, a local buckling at the compressed opening corners, and the appearance of cracks in the most tensile areas at the end of the load phase. The second results concern the cases with a frame stiffening solution and a configuration with a short double stiffeners. It is interesting to see that both cases are similar, with a more fragile behavior and a brutal cracking at the most tensile opening corners, after having reached the maximum load value. Then it can be observed a kind of residual strength which is maintained with a plastic plateau. Now, if we look at the behavior of opening composed of long stiffeners, for double stiffeners, the opening failure could not be obtained due to a limitation in the hydraulic jack maximal force. In the case of single-sided long stiffener, it is interesting to observe the formation of the plastic mechanism. Compared to the non-stiffened opening, we observe that the single stiffener allowed to increase the load carrying capacity of more than 50%. Those stiffeners clearly show the capacity to avoid local buckling and to strengthen significantly the openings. From those experimental results, it can be observed that the use of short stiffeners do not imply significant strengthening. Even worse, it appeared that the proximity of well beads with opening corners can imply a weakening of the tensile areas with the appearance of cracking and more fragile behaviors. Finally, one of the main results concerned the influence of long single-sided stiffeners. It shows that it provides more than a simple lateral support and allows to reach a full plastic strength of the reinforced T section, which is not considered in the existing design recommendations for the moment. In the next part of this work, we focused on the behavior of isolated opening under point load. Various configurations of opening, stiffening, and opening shapes have been tested. The first group coincides with the previous test, as it aims at studying the influence of stiffeners on the opening strength and stiffness against point load. The second group of samples aims at evaluating the influence of opening shapes on its behavior under point load, with hexagonal, rectangular, circular, etc. Mainly three failure modes could be observed during those tests. The first one, the crushing of the web panel. And then we could observe an elastoplastic bending of the upper member with a kind of local buckling of the adjacent web panels. And the last one, the plastification of the upper member in bending. Here are the failure modes of the different samples of group A. The only case with total plastification of the upper member corresponds to the sample with long double-sided stiffeners. The others mainly had a combination between bending and local buckling of the web panels. It is really interesting to look at the frame stiffening solution that is located at the upper part here, and where we observed the plastification of the member but kind of buckling even if we had this horizontal stiffener at the upper part of the member. Concerning the group B, all are composed of various opening shapes, and we observed mainly a combination of plastification of the upper member and local buckling of the web panel close to the opening corner, except for very large opening shapes like rectangular or large hexagonal shape. An interesting point to be studied is to evaluate the analytical approach that could be used to check an opening member at a point load. Thus, it has been decided to compare the ultimate loads and the stiffness with different simple analytical approaches. For example, considering a 3 or 4 point bending, a beam-supported beam, or a beam fixed at both ends. It can be observed that for the calculation of the ultimate load, considering the upper member as a beam fixed at both ends leads to unsafe results. The more adapted model seems to be the beam-supported beam under 3-point bending. However, as the failure mode concerns mainly also the buckling of the web panels, it implies that a simple plastic analysis may not be really adapted to deal with these problems. Again, concerning the definition of the elastic stiffness, it can be seen that the most representative case appears to be the beam-supported beam under 3-point bending. However, the opening behaves more like a verandil frame, so a better analytical model should consider this frame behavior. Here is the comparison of an equivalent frame with the numerical results, or the stress measured at the opening corner. It can be observed that the numerical results show a stress that varies from a fixed end beam model to a behavior of a beam-supported beam. And the frame behavior appears to be rather a good compromise. Now, if we look at the evolution of the maximum stress at the mid-length of the opening member, it is clear that the finite element model blue curve coincides more with the frame model curve than the fixed end beams, which is in red. So as a summary, we could see that the presence of long and short stiffeners increased significantly both stiffness and load carrying capacity of large web opening. long stiffeners provide more resistance of the opening as it reduces the global web panel instability. A plastic calculation appears to be not really well adapted for most of the cases that were studied due to web panel buckling. However, these comparisons allow to see that many of the samples show the behavior that is closer to a beam-supported beam rather than a beam with both ends fixed. However, a following study on the comparison between a frame behavior and the opening should be done, as it appears to behave more like the observed cases. To conclude on those two test campaigns, we could see that short stiffeners are not effective for verandil bending reinforcement. Furthermore, we could see that those stiffeners could imply a fragile behavior with brutal cracks that were observed at the vicinity of weld beads. Concerning long stiffeners with a sufficient anchorage length, one of the main results is the observation of long single-sided stiffeners. It appears that they do not simply avoid local buckling, but they also provide full plastic strength of a reinforced T-section. This can be a great issue in the future design rules because, for the moment, they do not allow to consider the single-sided stiffener in the plastic strength. Finally, we observed that considering a verandil frame appears to be a very satisfactory hypothesis for both the study of global beams and the study of single openings under point load. I thank you for your attention.